These three objectives will be covered in two parts. At the end of this Part 1 video, you should be able to relate the motion of a freely falling body to motion with constant acceleration, calculate displacement, velocity, and time at various points in the motion of a freely falling object, and compare the motions of different objects in free fall.
A falling object accelerates at a constant rate due to the force of gravity. As the object falls, the velocity will increase at a constant rate. The free fall acceleration due to gravity, symbolized by the letter g, is 9.81 meters per second squared at the Earth's surface. If only the force of gravity is acting on the object, then the motion is known as free fall. Air resistance is a force that slows a falling object. That is why a falling object can only be in free fall if it is in a vacuum. If an object like a spacecraft is in free fall, the occupants inside will also be in free fall and appear to float.
Chapter 2, Section 3, Falling Objects. Free fall. On August 2, 1971, a demonstration was conducted on the Moon by astronaut David Scott. He simultaneously released a hammer and a feather from the same height above the Moon's surface. The hammer and the feather both fell straight down and landed on the lunar surface at exactly the same moment. Although the hammer is more massive than the feather, both objects fell at the same rate. That is, they traveled the same displacement in the same amount of time. Freely falling bodies undergo constant acceleration. In Figure 3.1, a feather and a red apple are released from rest in a vacuum chamber. The two objects fell at exactly the same rate, as indicated by the horizontal alignment of multiple images. The amount of time that passed between each successive image is the same. However, as shown in the picture, the displacement in each time interval did not remain constant. Therefore, the velocity was not constant. The apple and the feather were accelerating. Compare the displacement between the first and the second images to the displacement between the second and third images. As you can see, within each time interval, the displacement of the feather increased by the same amount as the displacement of the apple. Because the time intervals are the same, we know that the velocity of each object is increasing by the same amount in each time interval. In other words, the apple and the feather are falling at the same constant acceleration. If air resistance is disregarded, all objects dropped near the surface of a planet fall with the same constant acceleration. This acceleration is due to gravitational force, and the motion is referred to as free fall. The acceleration due to gravity is noted with the symbols A sub g, generally speaking, or g, as long as it's on Earth's surface. The magnitude of g is about 9.81 meters per second squared, or 32 feet per second squared. Unless otherwise stated, this book will use the value 9.81 meters per second squared for calculations. This acceleration is directed downward, toward the center of the Earth. In our usual choice of coordinates, the downward direction is negative. Thus, the acceleration of objects in free fall near the surface of Earth is A sub g is equal to negative g, which is negative 9.81 meters per second squared. Because an object in free fall is acted on only by gravity, A sub g is also known as free fall acceleration.
In the 16th century, Galileo theorized that if there were no air resistance, all objects would fall with the same acceleration. Let's drop two objects into a room that has had all the air removed. A camera and a strobe light reveal that the two objects move together at all times. Notice also that the two objects move a greater distance during each time interval. The distance between two successive images is proportional to their velocity during that interval. So you can see here that the downwards velocity is constantly increasing. In a full second of fall, the velocity will increase by 9.81 meters per second. The acceleration caused by gravity near the surface of Earth is therefore 9.81 meters per second per second.
Acceleration is constant during upward and downward motion. Figure 3.2 is a strobe photograph of a ball thrown up into the air with an initial upward velocity of positive 10.5 meters per second. The photo on the left shows the ball moving up from its release toward the top of its path. The photo on the right shows the ball falling back down. Everyday experience shows that when we throw an object up in the air, it will continue to move upward for some time, stop momentarily at the peak, and then change direction and begin to fall. Because the object changes direction, it may seem that the velocity and acceleration are both changing. Actually, objects thrown into the air have a downward acceleration as soon as they are released. In the photograph on the left, the upward displacement of the ball between successive images is smaller and smaller until the ball stops and finally begins to move with an increasing downward velocity, as shown on the right. As soon as the ball is released with an initial upward velocity of positive 10.5 meters per second, it has an acceleration of negative 9.81 meters per second squared. After 1.0 seconds, meaning delta t is equal to 1.0 seconds, the ball's velocity will change by negative 9.81 meters per second, all the way to 0.69 meters per second upward. After 2.0 seconds, that is to say delta t is equal to 2.0 seconds, the ball's velocity will change again by negative 9.81 meters per second to negative 9.12 meters per second. The graph in figure 3.3 on the screen now shows the velocity of the ball plotted against time. As you can see, there is an instant where the velocity of the ball is equal to 0 meters per second. This happens at the instant when the ball reaches the peak in its upward motion and is about to begin moving downward. Although the velocity is 0 at the instant the ball reaches the peak, the acceleration is equal to negative 9.81 meters per second squared at every instance, regardless of the magnitude or direction of the velocity. It is important to note that the acceleration is negative 9.81 meters per second squared even at the peak, where the velocity is 0. The straight line slope of the graph indicates that the acceleration is constant at every moment. At this point, you should be starting to be able to relate the motion of a freely falling body to motion with constant acceleration, calculate displacement, velocity, and time at various points in the motion of a freely falling object, and compare the motions of different objects in free fall.